Okay, so it was fun in the Commons. There was a speaker, Kathy Mulligan. She mentioned that she thinks the space that we're working in right now is not working on a cryptocurrency level. We're not talking about currencies enough. We're doing tokenomics. And I think she is definitely onto something. The technology we're working on is basically economic networks. We're building our own nations with their own economic substrate. And it's built on open infrastructure. So we are the ones who can decide what we incentivize with the currencies we create, where we inject value, and how we inject value. So when we're working with COD, I think it's important to realize that everyone has a computer, and we can just inject currency into the system in which we all operate by giving it to people who contribute to distributed computing. So I've got 7 brief lessons here that I've learned over the years. I'm from Gridcoin. It's a coin that launched in 2013. We've incentivized BOINC since then. BOINC stands for the Berkeley Open Infrastructure for Network Computing. It's been running since 2002, 2003-ish, and as we all know, SETI at Home is 1999-ish. So we have been doing this for quite a while, and basically what Gridcoin does is mint a currency and distribute it to people who contribute to these BOINC projects. And BOINC still runs. There's 30 some odd projects running things from COVID vaccines to asteroid identification and mathematics, a bunch of whole different projects around the world. So when we think about incentivization, we have to think about the fact that when we incentivize something, we're going to get more of what we pay for and less of everything else. It's not just what we pay for. We're sacrificing something else. If I paid you to go get me a bottle of water right now, you would get out of your chair, so I'm incentivizing you both to get the bottle of water and to leave an empty chair. So when we incentivize people for distributed computing, how is that affecting the rest of the economic network? If we're only distributing currency that we're minting to distributed computing, what aren't we distributing currency to? What else could we be distributing currency to? Could we be using currency emissions to incentivize impactful science? Could we be using it to secure a blockchain? Anything like that. So it's important to keep in mind that COD is only one aspect of these economic networks we're building. A second lesson over these years, incentivization does not need to be monetary. So the way that Gridcoin distributes its currency is we choose a subset of these BOINC projects. So there's like 30 to 40 BOINC projects. We choose about 20 of them to distribute our currency to. The way we choose them is through a network-wide vote, and we're a very, very large network. We have 5,000 staking nodes. We have probably 20,000 distributed contributors, computing contributors, and BOINC itself has 200,000 hosts or more, so there's a lot of potential there. So we ask all these people to have a conversation about what is good science, essentially. So it's a very weird conversation to have, but in this network, we have scientists themselves, we have just regular people, we have people who are Web3 enthusiasts, and all array of background. So we end up creating a system where we're determining impactful science, or what we would call impactful science, without giving anyone money. They're not being paid to run an IE, which has been talked about a lot this week and is a very cool idea. But they're still getting to the same outcome. We don't need to pay them to do that. We ask them to determine what is valuable to them, and by doing that, they choose things that will add value to the network rather than detract value from the network. So they're not going to choose something that's trying to hack email passwords. They're going to choose something that's trying to cure cancer. That's the hope, at least, and it's worked so far. So, again, incentives don't need to be directly monetary. All right, number 3, like I said, BOINC has 200,000 hosts. Gridcoin itself has 20,000 people contributing to the network. And all these other distributed computing projects, once they get going, people are going to want to contribute computation cycles to impactful research or any type of computation project, particularly if they're getting paid. So computer data has the potential to be kind of one of the next onboarding ramps to crypto, Web3, whatever you want to call it, even to science. Everyone here, from what I could tell, has done SETI at Home, and SETI at Home probably played a major role in what you're doing now. So we need to think about maybe UX and UI and how we can build these systems to help these new people come in to a large open community of distributed computing, choose what they want to research or what they want to contribute to, and then just seamlessly integrate into this new economic reality where we have dozens of open economic networks working in parallel to determine what we as a society think is valuable at any given moment in time. Again, COD has the potential to bring 1 million people into the network fairly seamlessly. Lesson number 4, you get to define the values of your network with the incentives. So if Gridcoin, for example, only distributed currency to projects working on cancer marker research or something like that, that would be what we decide is valuable. That's the value of the network. If we distribute currency to both cancer marker research and math projects, finding large prime numbers, we determine those things are valuable. When you add everything that we're distributing currency to, you get the set of what the network thinks is valuable. That's a value set. You can distribute currency to essentially anything you want if you can figure out how the mechanism would work. There are easy ways to measure it. Distributed computing has challenges, but it's one of the easier ones because you can measure flops, cycles. You can distribute points that way. But you could reward the Olympics if you wanted. We could distribute currency to every gold medal winner in the Olympics from 1980 and on. And that would be part of our value set. It would be a very weird value set because cancer marker research, prime numbers, and Olympic sports. But it is anything you want to do. What you incentivize, where you distribute the currency, defines the values of the larger economic network in which you're working. So when we defined these incentive mechanisms for these projects that we're just starting to get going, I think it's important that we sit down and write down what our value sets are, what we think is valuable as a network. Lesson number 5, make things dynamic. So we have in a very envelope mathy sort of formula for how much computation power each project Gridcoin incentivizes. It's basically 1 over n plus x. N is the number of projects in the network. So if you have 10 Gridcoin to distribute to distributed computing projects, and you distribute 10 GRC a day, which is currency, each project would get, if you have 10 flops to distribute to a computing project, and you have 10 projects, each project would essentially get 1 flop. That's a very basic way to think about it. And then the plus X is anything else we want to add to it. So we can change that. We can make some projects worth more, worth less, try to get more people to do that work, and get fewer people to do a different project. We can make more people want to become Olympic athletes if we add that to our value set. Or when you bring in non-monetary incentives, you might be able to do something like what COVID-19 did when it first started going around. And we had this smoothing curve where we try to get people to distribute computation cycles to all these different projects, but all of a sudden there is this non-monetary incentive to contribute to projects that are trying to map the spike protein and otherwise analyze COVID-19 so we can develop a vaccine. And everyone, for a very brief time, stopped worrying about money and started working on the COVID-19 projects. They went very well. They discovered they mapped the protein very quickly, and we are where we are now. So there's that X factor that can manipulate where the currency is distributed, and then there's the aspect of it that's non-monetary, where if you can make people think that another aspect of the distribution or of the system is more valuable than another, they'll go do that thing, regardless of whether or not they're getting paid. So that's make things dynamic. And number 6 is a fun one, make things free by default. What the hell does that mean? So when you're distributing these currencies, there are specific projects that seem to be fundamental to advancing society, scientific projects mostly. So if we are developing systems that are still pay to store and still pay to compute, how is that any different than the system we currently live in? They should be able to store these data sets that build everything after it basically for free. We should be able to compute on them for free. And it's not free because nothing is free. It's essentially subsidized by the economic network that we've created. So we're generating currency, and we're distributing it to people who contribute to these specific tasks. Now, if you're working on a project that is going to be very profitable, that's a very translatable project or otherwise profitable, you should probably pay for compute, but it should be free by default. Any researcher, anyone who's building a foundational layer to society or the way economies work should probably not have to pay for it. They should just get access. I would love to see how that gets built, but I do think it's very possible. So number 7 here, when you do all these things, when you have an economic network that lets people decide what's valuable, what the value set of that economy is, and you make access to these resources essentially free, supported by the underlying economic layer, the central bank, if you will, that's minting the currency, you can develop an economy that's based on science. So if the science research is the value set, the scientific outcomes are what is injecting value into the system. If you have a ledger of scientific outcomes that are deemed valuable, if you store valuable data, that is what this makes people want to interact with that data, with that ledger. People will want to use the currency to interact with the data because they have to pay transaction fees at the root of the technology. So you're injecting value right into the ledger by just making people do science. So that is pretty much all I've got for you. It's a very quick talk. I want to go back to one lesson, though, and that's how important this field, computer over data, is in terms of adoption. It's bringing people in from almost every field to do one thing, which is compute, which basically runs the world already and is probably going to become much more important over the next 20 years. You get people who are working on economics, you get people who are working on software development, you get people who are working on every layer of the stack at the same time, in the same room, talking to one another and trying to figure all this stuff out. It's very important to be open to these perspectives. And in Gridcoin alone, for example, we are a very old coin that really did not start with any pre-mine. There was no ICO. There was no money. And we've survived for almost 10 years at this point solely because people want to do this. They are very interested in making this work. They want science to be the base of economy. They don't want debt to be the base of economy. It doesn't make sense. We want to make the world a better place, and if in order to make money, I have to make the world a better place, that's awesome. That would be so great. Imagine every rich person right now, today, who instead of having to extract value from the system in order to become rich, had to produce scientific outcomes that made the standard of living for everyone around them better in order to get rich. They can still be as rich as they want, but the way they got there was to make everyone else's life better, to make more medicine, to make more faster cars or better, more efficient cars, anything like that. That would be a world that I think a lot of people want to live in, and Gridcoin is an example of why I believe that, because it just still exists. There's no reason this thing should exist anymore. It was a very bad set of code. It had very interesting and, let's say, poorly designed economic systems. And we're going to hear from Levi in a second, who has gone from Gridcoin to just contributing to Gridcoin to developing a very interesting model for how to incentivize distributed computing across many different platforms. Our developer is just a guy with a lot of time who's really, really smart. And he has a very serious job outside of Gridcoin. Our community just has families who they just want to see this work. No one's paying them. It's insane. So, point being, an economy based on science is something that will bring thousands of people in here to build because it's something worth building, not because they're getting paid for it. And it's very inspiring to see all these projects that have been presenting today, and there's been almost no talk of tokens. There's no pay model. We're going to build this thing that's going to fix this problem, and we have this solution. It's very nice to see, so I hope that's the way the space keeps going. And with that, I don't know, anyone got any questions? There's not much to ask about, but...
Hi, my name is Levi. As John said, I come from the Gridcoin community. And today I'm going to tell you about incentives in distributed computing. So, John mentioned that Gridcoin's incentive mechanism basically works by taking a pool of rewards, dividing it by the number of projects, and then handing it out proportionally to the people who compute those projects. In practice, what this does is it leads to very, very disparate rewards for crunching different projects. So for example, with the exact same set of hardware, you could get about 5 times as many rewards as you would another project, and that really depends on how many people are crunching that project. The question is, can we find a better way to do this? Can we find an axiomatic approach to defining block rewards or rewards more generally for this network? And really, what we're asking is, can you find an incentive-compatible allocation rule that doesn't pit a cruncher's preferences against what their hardware is best suited for? So basically, if you really, really believe that you really want to work on the cure for cancer, but your hardware is really best suited for some other project like mapping the Milky Way, your economic incentives are not aligned with your financial incentive, or rather, your financial incentives are not aligned with your personal beliefs. And in game theory, algorithmic game theory and mechanism design, you usually want to be able to align those. You want people to be able to express their honest opinions and you want to design truthful mechanisms, right? You want people to say, this is actually what I believe, this is actually what I want to have happen. This is pulled from David Anderson's paper. David Anderson was the founder of BOINC. BOINC has a credit system, and ideally it achieves the following properties. So it should be device neutral. So that means that similar jobs should get about the same rewards regardless of the host and computing resource on which they're processed. It should also be project neutral, and that means that a given device, any machine, should be able to get about the same amount of rewards regardless of which project it crunches. And the third is that it should resist cheating, right? So you shouldn't be able to cheat the reward mechanism. This is being pulled from, this is from a paper by Shi Chen, Christos Papadimitriou, and Tim Roughgarden on an axiomatic approach to block rewards. And basically, this is, of course, right here, this is your expected reward from every block in the Bitcoin network, right? So it's your hash rate divided by the hash rate of the whole network, and that's your expected payoff for every block. And this has a few very nice properties. It satisfies non-negativity, budget balance, symmetry, civil proofness, and collusion proofness. Those aren't really important for right now, but I think they demonstrated that the Bitcoin proportional allocation rule is the only rule that would satisfy those in this problem setting. And so in BOINC and in Gridcoin, we have a really highly heterogeneous computing environment, right? So we have tons of different types of computers. We have everything from mobile phones to Raspberry Pis and SBCs. We have different, obviously desktops and laptops, and we have AMD and NVIDIA GPUs. We have Intel and AMD and ARM CPUs, and we have that combined with many different operating systems, along with different BIOS settings, different motherboards, RAM. It goes on and on, right? So the space of hardware configurations is absolutely massive, and simultaneously, the computing environment, there's also a lot of heterogeneity in in the computing tasks, right? So mapping the Milky Way versus trying to find the form of the spike protein on COVID versus doing simulations for the Large Hadron Collider, et cetera. There's just a really, really different, really, really mixed set of computational requirements that these projects have. And so the question is, can we find an analog to this proportional allocation rule in this heterogeneous setting? So this is the generalization, and for now, let's just consider tasks, computational tasks that require a CPU. This does generalize, but I'm trying to keep things simple. So the basic idea is to treat the entire network as one massive supercomputer, right? And so what you ask is, let's say that you take every CPU on the network and you focus it on project A. How many computational units are you going to get done in some amount of time, right? And then say you focus in on project B. How many computational units are you going to get in some amount of time? And then you basically set each of those equal to each other. So basically, this would take the form of, X units of computation type A are equal to Y units of computation type B, right? That's how you relate work units and tasks from different projects to each other. And equivalently, this is also like taking the average of all the computers on the network. It's the sum versus the average. Of course, it's just a scaling factor, so it's pretty much the same thing. So that's great. So now that we have a way to equate work units from different projects, we can construct a universal task, a universal work unit. And since we can compute any type of computation to units of this universal task, we can calculate the output of the whole network in terms of one number, right? In terms of this, in units of this universal task. And then to calculate the cruncher's rewards, we just take their output on whatever projects that they were crunching. And really, it's applications in BOINC, but I'm trying to keep things simple. We divide it by the output of the whole network, right? So it's whatever you do in terms of this units of universal task divided by the same, whole output of the network in units of this universal task, and that's the proportional allocation rule, right? And so this is basically the same as the Bitcoin proportional allocation rule. And since we're starting with a heterogeneous set of tasks, this is actually a multidimensional generalization, right, of the Bitcoin proportional allocation rule, right? Because you can think of it like instead of having just SHA-256, we're now introducing different types of functions, ETH hash or whatever, just we have a large set of different types of computations, and we're kind of collating them all into one. We're trying to find a way to equate them with each other. So what kind of behavior does this reward mechanism incentivize? So in order to maximize rewards, crunchers should maximize their output in terms of the universal work unit, accounting for their energy consumption. So this has an interesting implication. And so crunchers may be incentivized to maximize their rewards, for example, by overclocking their hardware. Now, this may or may not be the case depending on how much your electricity costs. Because if you're only getting a 10 or 20% gain on your by overclocking, but your electricity costs are what we tend to have in most of the world, this is not going to be. It probably won't be worth it. Basically, you'll probably end up losing money, but it might have that incentive. And also, that in particular might yield a lower task completion rate per unit of energy consumed, and it also should shift the burden of the carbon emissions from over the life of this hardware from the production of the hardware actually to the consumption and use of the hardware over its lifetime. And this can actually be leveraged to make better use of already existing hardware rather than the production and purchase of the newest hardware that we have. Also, it's also important to remember that while this is somewhat of an edge case, in general, the reward mechanism basically incentivizes using your hardware as best as possible relative to all of the other hardware on the network. In BOINC, I won't go into the details because it's complicated, but in BOINC, it's very difficult to gather the data necessary to actually compute that equivalence ratio, the way that we equate units of one task, units from one project to another. And so we have to approximate it, right? And so there's two ways of doing this in the paper. One is using linear regression, and another one is constructing a hardware profiling database. The linear regression approach would take a bit too long to explain, although it is very interesting. If you're interested, you can read the paper. But the hardware profiling database, I think, would be of great interest to a lot of people in this audience. So it's really not that hard to construct a hardware profiling database, right? You just need a set of benchmarks that you compute on. You basically do that for every machine on the network. And then what you also want is an approximation. You would also want data on how that same machine performs on the actual tasks from these projects, right? And then it's as simple as just running a machine learning algorithm using like a nonlinear regressor or deep learning or whatever to basically map the hardware benchmarks to outputs on each of these projects one by one. And in that way, you can approximate what the entire network can do. And in fact, you can infer what any new type of hardware can do in the future. And this would be of immense use to many different groups of people, researchers, companies, other compute providers, people on the network who are interested in what if they really care about mapping the Milky Way, what's the best hardware to buy for their next setup. So anti-cheating mechanism, right? So how do we prevent cheating? So this is going to just be a really basic probability and game theory approach. It could be that ZK proofs and other methods might yield better approaches in the future. I don't know enough to say. But this is just a really, really basic analysis. So consider a single machine that's receiving a stream of tasks. Some of these tasks can be replicated and sent to other machines to double check the results, right? Because you generally want to have some kind of consensus on whether these results are accurate. But you also want to reduce the amount of replications of jobs because that's a massive waste, right? So you can just imagine a machine. It's the only one crunching each of these tasks, and then with some probability p, you're going to replicate that, and I'll get to that in the next slide. But basically, the approach is you have a reward pool for every task in the network. For every task that's being sent. And then basically you just divide that reward pool amongst all the crunchers who who did that task honestly, right? So if one person crunched it, then they get all of the rewards. If two people crunched it, each of them get half, and so on and so forth. And so clearly this incentivizes you to be the only person who's crunching this task, right? So you want to be honest, and you want to be the only person crunching this. And so how does the anti-cheating mechanism work, right? So suppose that a task is replicated with probability p and has a total reward pool r. So if we can go back in time and check prior tasks that were completed, we can basically calculate the number of tasks necessary to go back and recompute the tasks such that it's not worth cheating, right? So for example, suppose this p is 5%, 0.05, and you basically, the chances of getting caught is going to be geometrically distributed, right? It's just, on every single task that you're being sent, there's a 5% chance of being sent a replicated copy, and that means that in expectation on the 20th task, you're going to get a replicated copy sent to someone else. And if you're cheating throughout all of those and you finally get caught, what basically happens is you can go back and look at the past. So this, if we could just do the 1 over p here, so that's 20. I'm going to ignore that -1. So this is 2 times 20, which is about 40. And basically, you can go back to the last 40 tasks, recompute them on another node because you think that this node is cheating, right? Because you didn't get the proper results that you thought you would. And then basically, if that node was being honest, then the equivalent of the 40 tasks where you get half the credit is the same as 20 tasks where you get all of the credit, and so it wouldn't have been worth to cheat to begin with. And then if we cannot go back and recompute tasks, then you can just use a deposit, and you can slash the deposit. This is the equation. The math is in the paper. So finally, we can get to the original goal, right? So remember, the original goal was, well, I have all of these personal preferences, all of these personal beliefs about what types of computations I think are important, but my hardware might be better suited for other types of projects. And so what can we do? So intuitively, if you have some hardware and you really like some project, but my hardware is better on your project, but your hardware is better on the project that I like, we should trade, right? Right, because we could both benefit by doing this, right? So because the amount of tasks we compute from each of those projects increases, our overall profit would increase as well relative to if we crunched what we believed. And so intuitively, you can kind of just virtually trade your hardware. And in the simple case of one cruncher owning one machine that can only crunch one application, this problem reduces to a very well-known problem called the housing market problem with endowments. This is solved by an algorithm called top trading cycles, which is course selecting and strategy proof. Strategy proof, some of you might know it better by dominant strategy, incentive compatible, plus individual rationality. Individual rationality meaning that it makes sense for you to participate in this game, basically. And course selecting basically means that no coalition of agents has an incentive to deviate and form their own group away from this game, right? So, and that includes coalitions of size 1, which actually means individual rationality, and that also includes a coalition of the size of everyone on the network, which means that it's Pareto efficient. So course selecting also implies individual rationality and Pareto efficiency. Unfortunately, this actual problem is way more complicated than that because, of course, one cruncher can definitely own more than one machine, and of course, that one machine can crunch more than one application at a time. So the generalizations of this problem exist, but the general setting that I just described is an open problem. There is a really, really interesting approach in a paper that was published as a preprint published in the middle of last year that used parameterized linear equations to solve the problem. So basically the way this method, the top trading cycles method, basically the way it works is, you could think about like the two-person trade, but now imagine you have a bunch of people and, maybe we can just trade in a circle, right? And that's kind of how top trading cycles works, and then, it clears the people who traded and it continues the algorithm. In the parameterized linear equations approach, they kind of drop this idea entirely, and so it actually enables a much larger generalization than this kind of older method. So environmental assessment. So basing the reward mechanism on the equivalence ratio incentivizes using hardware on the application on which it's most efficient relative to the rest of the network. However, like I said earlier, depending on the electricity costs, they may not incentivize achieving the highest task output per energy input. So you could, again, think about overclocking. And again, it really depends on how much energy you're consuming. So the anti-cheating mechanism obviously reduces the number of replicated tasks, and that reduces the energy consumption per task completed. The virtual hardware trading reduces the energy consumption per task as well, right? Because when you're trading hardware and you're using more efficient hardware, clearly, you're going to use less energy in computing those tasks. So regarding carbon neutrality, so you can recover waste heat, and we should be doing that. Unfortunately, you're not really going to get better than heat pumps. That's just physics. Basically, the question is, does the social benefit of having a massive decentralized supercomputer outweigh the environmental costs? And I would argue that they do well, we don't have time for that, but if you want to come talk about it later, I would definitely argue that it does, especially if we're recovering the waste heat and we're not having all this massive computational power, concentrated in a few large companies and governments. And also, additionally, you can directly incentivize projects that are environmentally focused, like climate prediction and maybe something in material science for better batteries or solar panels or whatever. And you can avoid curtailment by using excess energy to crunch. So curtailment is when you have somewhat of an overproduction of energy from renewable energy sources, and sometimes you kind of just have to throw it away. Well, actually, you can use it here. You can use it and not waste it. And you can also direct minted currency towards the sustainability project. So you can use the actual network, either individually, or you can use the actual network to direct some of the currency towards sustainability. So this is the title of the paper: Incentivizing Energy Efficiency and Carbon Neutrality in Distributed Computing via Cryptocurrency Mechanism Design. I might change that title if you're watching this in the future. I hope you're well. You can just look up my name on Google Scholar and you will probably find this paper. These are the two references, the two papers I cited, and I really want to thank the Gridcoin community, because it's really just such an open community full of welcoming people who are always ready to help. In particular, I just wanted to thank two people quickly. So one of them is Jim Owens, who is the lead developer for Gridcoin. I've had many conversations with him over the years, and he's been incredibly, incredibly helpful in thinking about a lot of these problems. And I also wanted to thank user Scribblemaniac on Discord for pointing out a problem in my algorithm, a flaw actually that I addressed in this presentation, and so that was very useful. So yeah, thank you.